Hello and welcome to our presentation. Through this video we will give a pictorial representation of the basics of X-ray crystallography and then move on to answering our question, how does molecular replacement work? This will be done with the help of our artistically gifted assistant Jack. Here we have a general X-ray crystallography method. X-rays from a source are fired at a crystal that we have previously crystallized and these photons are scattered. The diffraction pattern that results due to the arrangement of atoms in the lattice is recorded, with the number of electrons present in the structure being proportional to the strength of the scattering. A Fourier transform is then done which provides an electron density map. This is where we run into our problem, however, the phase problem. Here we see Jack laying out the Fourier equation. As you can see, this equation requires two variables, the amplitudes, the intensity of the diffraction pattern obtained, and the phases, the position of a photon at a point in time. X-ray crystallography is a method that gives the amplitude but not the phases, as due to the nature of the constructive and destructive interference, data can be lost. As the drawing shows, in-phase waves are waves that are identical in nature and construct, and so create a diffraction pattern. And out-of-phase waves destruct and cancel each other out, so do not provide a diffraction pattern. This is where the phase information can be lost. The method used to get around this problem is molecular replacement. Once the sequence of our protein, known here as protein X, is known, we have to find similar proteins with more than 20% sequence identity, resulting in a similar folded structure. It is estimated that up to 3/4 of all structures use molecular replacement to find phases. Here is an example of the process with shoes, because what's the difference between a shoe and a protein really? The shoe with the Nike tick is our protein X. The other shoe outline is the more than 20% similar protein, and this is the Adidas shoe. Using complicated molecular replacement programs, the amplitude from protein X and the phases from the sequentially similar protein are combined. Here we see the outlines of the shoes fitting each other like gloves, well, shoes for that matter. They're fairly similar, with the analogous protein giving the phase similar to that of protein X. The problem is that phase identity dominates the reconstruction of electron density, so the structure that we have determined does not equate to the true structure completely. There are methods to remove phase bias, such as prime and switch phasing, however we will only touch on this here. Finally, we can see how molecular replacement programs match the orientation of the two proteins, as demonstrated with the good old shoes. The rotation of the shoes is analogous to the way that these molecular replacement programs cycle through all possible orientations and positions of the model in the unknown crystal, and to find where the predicted diffraction best matches the observed diffraction. Two main ways to compare and superimpose these outlines is the Patterson and maximum likelihood method. More about these can be found online and in our references. Once this process has been achieved, the phases of the two shoes or crystals are combined.